Hello everyone, we start section 5.2 Mathematical Induction part 1 by introducing the principle of mathematical induction. Let's assume that P of n is a property that is defined for all the integers n, and let a be a fixed integer. Okay, so we have n as an integer and a, which is a fixed integer. Now suppose the following two statements are true. The first statement is P of A is true. Okay, so the first thing that we know is P is true for one fixed integer, which is A. And the second thing that we know is that for all integers k which are greater than or equal to A, which is that fixed integer, if P of k is true, then we can conclude that P of k plus 1 is true. Okay, so that's the second thing that we know. So the second thing is a universal conditional statement. It's universal because we're saying for all integers k, and it's conditional because we say if P of k is true, then P of k plus 1 becomes true, right? So based on these two given assumptions or premises, we can conclude based on mathematical induction that for all integers n greater than or equal to that fixed integer a, P of n is true. So if I want to explain the concept of mathematical induction more clearly, I can use the example of dominoes. Let's assume that we have an infinite number of dominoes, number 1, number 2, number 3, number 4, all the way to infinity, okay? And let's assume that we want to prove that all dominoes will fall under two assumptions. The first assumption is the first domino falls backward. Okay, so someone hits the first domino and it falls backward. And the second assumption that we have is if a domino falls backward, it pushes the next domino backward too, right? So for example, if we have a k domino right here, k plus 1 is the next domino that we have. If k falls backward, it pushes the domino number k plus 1 backward too, right? So if we have these two assumptions, we can conclude based on mathematical induction that all of the infinite number of dominoes that we have will eventually fall backward, right? So for any given domino, no matter which domino it is, it will fall eventually, right? Okay, so in the previous slide, we introduced the concept of mathematical induction. Now we are going to formally introduce the method of proof by mathematical induction, right? So consider a statement in the form of a universal statement which says for all integers n greater than or equal to a, the property P of n is true. To prove such a statement, we need to do these two steps. The first step, which we call the basis step, we need to show that P of A is true. So this step means the first domino falls. And the second step, which is called the inductive step, basically says that we need to show for every integer k greater than or equal to A, if P of K is true, then P of K plus 1 becomes true. So this is a universal conditional statement that we must prove it if we want to prove the original statement, which was a universal statement for all integers n greater than or equal to A, right? So the inductive step basically says if the kth domino falls backward, then the next domino, the k plus 1th domino, it also falls backward. Because here we say for all k greater than or equal to A, if P of k is true, then P of k plus 1 becomes true, right? So to prove the second step, which we call inductive step, we have a assumption which basically says P of k is true, right? Because as I said, we are dealing with a universal conditional statement, and in the conditional statement, the condition is P of k is true, right? Where k is any particular but arbitrarily chosen integer with the inequality k greater than or equal to A, right? So this condition is called the inductive hypothesis. That's the assumption that we need to consider to be true if we want to prove the inductive step. If we want to prove that P of k plus 1 is also true, right? So, and again, we have to, in order to prove the inductive step, we first need to assume that P of k is true for any arbitrarily chosen k, and that is greater than or equal to A, and then after that we need to try to prove P of k plus 1 using the assumption that P of k is true, right? So this is the second step, and if we prove both steps, the basis step and the inductive step, then we can claim that we use the method of proof by mathematical induction to prove the original universal statement that was given here. So in order to illustrate the method of proof by mathematical induction, let's see an example of the book, proposition 5.2.1, which basically says for all integers n greater than or equal to 8, n cents can be obtained using 3-cent and 5-cent coins. So that's what we need to prove using mathematical induction. So as we said, we need to follow two steps. The first step, which is called the basis step, basically says we need to show that P of 8 is true, right? So that's the first step. In order to show that P of 8 is true, because 8 is the the constant A that we had in the previous slides. So in order to show that P of 8 is true, we need to show that 8 cents can be obtained using 3 cents and 5-cent coins, which is obviously true because 8 cents can be obtained using one 3-cent coin and one 5-cent coin, right? So there's no problem with the first step. Now let's go to the second step, where we need to show that for all integers k greater than or equal to 8, if P of k is true, then P of k plus 1 is true. Let's see how we prove the inductive step, which is the second step in this question. So let's first see the inductive hypothesis. This is a universal conditional statement, so you have to first know what the condition is. the condition is P of K is true, right? So K cent, this is P of K. Which basically says K cent can be obtained using 3 cent and 5 cent coins. So we need to consider this hypothesis to be true if we want to prove the inductive step, right? So this is called the inductive hypothesis of our problem. Now we are going to use this hypothesis to prove that P of K plus 1 is true. What is K plus 1? What is P of K plus 1? P of K plus 1 is this statement. It says K plus 1 cent can be obtained using 3 cent and 5 cent coins, right? So instead of K, I just put K plus 1. Okay, so in order to prove P of K plus 1, we use the method of proof by division into cases. We have two cases here. In the first case, we assume that there is a 5 cent coin among those used to make up the K cent. So as we know from inductive hypothesis, K cent can be obtained using 3 cent and 5 cent coins, correct? So the first case basically says there is a 5 cent coin among those coins that will add up to K cents. So in this case, we only need to replace a 5 cent coin by two 3 cent coins, and the result will be K plus 1 cent. Why? Because we remove 5 and we add two 3 cent coins, which is 6 cents. So we remove 5 cent and we replace it with 6 cent, which is two 3 cent coins, right? So we remove 5, we replace it with 6 cents. It means that we add 1 more cent to those K cents that we had before. So we have the total of K plus 1 cent. So the proof of the first case is done, and we can go to the second case. Okay, so in the second case, we assume that there is no 5 cent coins among those who used to make up the K cents, right? And since K is greater than or equal to 8, here you see we assume that K is at least 8. So we must have at least three 3 cent coins to make 8 cents. Why? Because if we don't have three 3 cent coins, we obviously assumed in the second case that there is no 5 cent coins. So we can conclude that we only have either two 3 cent coins or one 3 cent coins, or we have no coins. Okay, and in each of these three cases we have less than 8 cents. So it's obviously impossible that we have less than 3 cents in the second case. So we have to have at least 3 cents to make K cent where K is greater than or equal to 8. So as a result, we can remove those 3 cent coins that we just proved their existence and replace them by two 5 cent coins. And as a result, we will have K plus 1 cent. Why? Because we removed three 3 cent coins, which is 9 cent, and we added two 5 cent coins, which is 10. So we remove 9 cents and we add 10 instead. So we had K before, and then 10 minus 9 is 1 cent, right? So K cent from what we had before plus 1 cent would result in K plus 1 cent. in total, and as a result we are done with the proof of the second case. So since we proved both cases of the inductive step, then we can conclude that we are done with the inductive step. So we were done with the first step here, and now we are done with the second step here. So we can conclude that we proved the proposition 5.2.1 using the proof by mathematical induction. The next thing that we need to prove is theorem 5.2.2, which basically says sum of the first n integers is equal to n times n plus 1 divided by 2 for all integers n greater than or equal to 1. So in order to prove this theorem using mathematical induction, we need to first define the property P of n in the following way. We say P of n is this equation. We say 1 plus 2 plus 3 all the way to n is equal to n times n plus 1 divided by 2, correct? So this is P of n. As the first step or basis step, we need to prove that P of 1 is true, right? P of 1 is basically the left hand side of the equation is only 1, and in the right hand side we have 1 times 1 plus 1 divided by 2, which is 1. So both sides of the equation that defines the property of P of n is true for n equal to 1, so we can conclude that P of 1 is true. So we are done with the first step. Usually the first step is the easiest step, so in order to finish the proof, we only need to prove the second step, which is a universal conditional statement. Basically says for all integers k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. So the inductive hypothesis is P of k is true. P of k is an equation like this. It's 1 plus 2 plus 3 plus all the way to k is equal to k times k plus 1 over 2. Okay, so we must show that this equation is true for k plus 1. So when we continue this summation one more step, we will reach to P of k plus 1, which basically says the summation of numbers from 1 to k plus 1 is equal to this formula. So 1 plus 2 plus 3 all the way to k plus 1 is equal to the summation of all numbers from 1 to k plus k plus 1. So I separated the last term from the other terms that we have. The first k terms would be equal to k times k plus 1 over 2 according to what we have in the induction hypothesis. This equation, I'm going to call this equation equation 1, and I'm going to say this is equal to this because of equation 1. Okay, and we have k plus 1 at the end, so it's going to be equal to k times k plus 1 divided by 2 plus the last term, which is k plus 1. So if you factor out k plus 1, what you get is this formula, which is basically this formula, the original formula that we are going to prove, with the only difference that instead of n, here we put k plus 1. So we conclude that we have proved that P of k plus 1 is also true, and this means that we are done with the inductive step. Since we are done with both steps, we can claim that we have proved theorem 5.2.2 using proof by mathematical induction. Alright, so the last proposition that we are going to prove using mathematical induction in this section is this statement. It says, for all integers n greater than or equal to 0, 2 to the power 2n minus 1 is divisible by 3. Okay, so that's the original statement that we are going to prove it using mathematical induction. So to use mathematical induction, we need to first define the property P of n. So don't forget, this is always the first step. P of n is what? Is this sentence. Is 2 to the power 2n minus 1 is divisible by 3. Okay, so we have defined P of n. Now let's start from the basis step. This step number 1, which basically says P of 0 is true. In order to establish P of 0, we just need to replace ny0 in P of n, which says 2 to the power 2 times 0 minus 1 is divisible by 3. So 2 to the power 0 minus 1 is equal to 1 minus 1 or 0, and since 0 is divisible by 3, we can conclude that P of 0 is true. Now let's go to the inductive step. In the inductive step, we need to prove a universal conditional statement in the following form. We can say, for all integers k greater than or equal to 0, if P of k is true, then P of k plus 1 is also true. So let k be any integer with k greater than or equal to 0, and suppose that 2 to the power 2k minus 1 is divisible by 3. This is called the inductive hypothesis. Okay, so in the inductive hypothesis, we know that 2 to the power 2k minus 1 is divisible by 3. Now, using this hypothesis, we need to show the same property for n equal to k plus 1. So we need to show that P of k plus 1 is true. The P of k plus 1 becomes 2 to the power 2 times k plus 1 minus 1 is divisible by 3. In order to show that, we need to use, obviously, the inductive hypothesis, right? So by the definition of divisibility, and based on the inductive hypothesis, we can say 2 to the power k 2 to the power 2k minus 1 is equal to 3r for some integer r, right? That's the definition of divisibility by 3, which is an integer. So we can simplify 2 to the power 2 times k plus 1 minus 1 using basic algebra and the fact that 2 times 2k minus 1 is equal to 3r, and we can factor out the 3 to reach this expression, which says 2 to the power 2k plus 1 minus 1 is equal to 3 times 2 to the power 2k plus r. And since 2 to the power 2k plus r is an integer, then we can say that the number 2 to the power 2k plus 1 minus 1 is also divisible by 3, and basically in this point we are done with the proof of the inductive step. And since we have done the proof of both the inductive step and the first step, so we are done with the proof of the whole proposition using mathematical induction.